Page 3 of MHL, Chapter 16, Complex Numbers. Number 6. Use the result to show that this is equal to this. Okay, so let's see. If I have z1, z2, z3 modulus, isn't that equal to z1, z2 in parentheses times z3 modulus? And if z1, z2, the product of that is also a complex number, right? Then I could rewrite that as z1, z2 modulus times z3 modulus, right? I just used this rule here. I took z1, z2, which is a complex number, and I left it by itself inside the modulus. Now that I have this, I can go back and use this, right? And now I know that z1, z2 modulus is equal to z1 modulus z2 modulus z3, okay? So there you go. Now let's do it for 4. It's going to be similar. I could divide this up into 2 sets. I could divide it into 2 complex numbers multiplied together, so that would be equal to z1, z2 modulus times z3, z4 modulus, and that's equal to z1 modulus, z2 modulus, z3 modulus, z4 modulus. Okay? All right. Generalize your results from A. So that would mean that if I have z1, z2, z3, zn modulus, that is equal to z1 modulus, z2 modulus, z3 modulus, zn modulus. For n greater than or equal to, or we'll say for n is an element of positive integers. C. Use the principle of math induction to prove your conjecture in B. Okay, so first of all, our proposition is this here. Then I'm going to create proposition n equals 1, which would be z1 modulus is equal to z1 modulus, which is true. So P1 is true. And now I'm going to assume that PK is true. So PK is Z1. I'm just going to do this here, except instead of N, I'm going to put K. So Z1, Z2, Zn modulus is, or Zk modulus is equal to Z1 modulus times Z2 modulus, Z3 modulus, Zk modulus. Okay, so we assume that's true. Then we're going to look at the k plus 1th case. So now Z1, Z2, Zk, Zk plus 1, that is equal to Z1, Z2, blah, 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 to Zk, parentheses, Zk plus 1, is equal to Z1, Zk modulus times Zk minus 1 modulus. And Z1 to Zk modulus is equal to this. So we've proven it. Z1, Z2, all the way to Zk plus 1. Okay? So then we can say if P of 1 is true and P of k plus 1 is true, whenever P of k is true, then P of n is true for n is all positive integers. Okay? All right. Hence prove that z to the n modulus is equal to z modulus to the n. So basically what this is saying is take the general case where you have a bunch of different complex numbers multiplied together, and let's look at the specific case where you have one specific number multiplied times itself multiple times. So it says to prove that. Well, we could just take the result that we had before, which is this result here, right? And then we'll say, okay, now Z1, Z2, Z3, all the way to Z to the K, or Z to the N, is equal to Z. And if that's the case, then we could say that Z times Z times Z times Z, all the way to the last Z, is equal to Z modulus to the N. Or maybe before I'd say that, I'd say Z modulus times Z modulus times Z modulus, all the way to Z modulus. And I have n z's multiplied together inside the modulus, and I have n moduluses multiplied together n times. So I've proven it. E, find z to the 20 modulus for z equals 1 minus I square root of 3. Okay, so that would be a real pain to multiply that together times itself 20 times. But we do know that z to the 20 modulus is equal to z modulus 20 to the 20th. So we know what z modulus is, right? If it is plus 1 on the real axis and minus square root of 3 on the imaginary axis, that's basically making a 30, 60, 90 triangle in that direction there. So the modulus is going to be 2, right? If this is 1 and this is square root of 3, this has to be 2. So the modulus is going to be 2. So we know it's, this isn't a 2, it's a z. So 2 is the modulus to the 20th power. So that is our answer, 2 to the 20th. All right. 7. Given that the modulus is 3, use the rules ZW modulus equals Z modulus W modulus, and Z divided by W modulus equals Z modulus divided by W modulus to find modulus of 2Z. So if I have modulus of 2Z, then I could rewrite this as modulus of 2 times the modulus of Z. And the modulus of 2 is just 2. The modulus of Z in this case is 3. So it'd be 2 times 3, 6. C, I have the modulus of 1 plus 2i times Z. And I could separate that into two parts. I could have modulus of 1 plus 2i times the modulus of Z. Remember, the modulus of Z is 3. So that would be equal to, let's see, the modulus of 1 plus 2i is, let's see, square root of 5. 1 squared plus 2 squared is 5 square root. So square root of 5 times modulus of Z, which is 3. E. Modulus of 1 over Z is equal to the modulus of 1 divided by the modulus of Z. Modulus of 1 is 1. Modulus of Z is 3, so 1/3. Number 9. Suppose Z is a complex number. Find modulus of Z if the modulus of Z plus 9 is equal to 3 times the modulus of Z plus 1. Remember that identity that Z modulus squared is equal to Z conjugate? So I think we can use that. Let's square both sides. So Z plus 9 modulus squared is equal to Z plus 9 times Z plus 9 and conjugate of Z. We have 9 Now z plus 1 times z conjugate plus 1. Now let's multiply things out. So z conjugate plus 9z plus 9z conjugate plus 81 equals 9 times z conjugate plus z conjugate plus 1. Let's distribute the 9. 9z conjugate plus 9z plus 9z conjugate plus 9. Now let's cancel out like terms. 9z and 9z conjugate cancel out. We're left with, let's see, zz conjugate. We have 8zz conjugate if we subtract 1 zz conjugate from both sides. And we have 72 on the left if we subtract 9 from both sides. Then we have 9 equals zz conjugate, which means that z squared equals 9. Z conjugate squared is 9. So z conjugate is equal to 3. And that's it for this page.